Hello guys, so today I'll be solving this problem which is last day where you can still cross. Okay, so this problem it's recorded as a hard problem, but it's not that hard. Okay, um, it's basically the idea to solve the problem that is a new concept maybe for a couple of you guys. That's why it is labeled hard, but yeah, it's not that hard. So yeah, the problem states that we have been given a one-based binary matrix where 0 represents land, 1 represents water, okay, and we have been given row and col, which basically represent the number of rows and the number of columns in the matrix, okay. Then initially on day 0, the entire matrix is a land. However, each day a new cell becomes flooded with water. Then then we have been given this cells data structure, which represents which cell in the grid has flooded. So, and yeah, one more thing, all of the coordinates are one base indexing. So if we want to process them in, we may need to convert into zero base indexing, or you guys are like feel free to use one base indexing itself. Then yeah, so yeah, we have been given this cell matrix which basically represents on which day which cell was flooded. Then the question is asking us to find the last day that is possible to walk from the top to the bottom by only walking on land cells. Okay, so you can start from any cell in the top row and at any cell in the bottom row. You can only travel in four cardinal direction, left, right, up and down. So yeah, we basically need to return the last day. So if I draw out what this problem is saying, so let's take this example. Okay, so let's say this is my grid cell. So let's say so yeah, this is 0 0 0 0 0 0 0 0 0. Okay, so we have been given this calls. Okay, 0 1 2, then oopsie, yeah, then we have been given this row. Okay, so yeah, then we have been, so this is our matrix. Here 0 represents land, which basically means all of them are land on the day 0. Okay, then we have been given this cells. Okay, so if I draw out this cell, so I have 1 2. Okay, so this is on day 1, 1 and 2. Yeah, I also need to convert them into one base indexing. Okay, so let's call it 1 2 3, and this is 1 2 3. Okay, so yeah, day 1 cell 1 2 becomes flooded. Then we have been given 2 1, that's on day 2, 3 3, 2 2, 1 1, then 1 3, then 2 3, then 3 2, and then finally 3 and 1. Okay, so yeah, these are basically the days on which which cell was flooded. So this 1 2 3 4 5 6 7 8, and this is on the 9th day. Cool. So let's see, uh, let's choose this. Okay, so yeah, so on day 1 1 2, this cell becomes flooded. Okay, I will just complete this matrix. Okay, so yeah, on day 1 this cell becomes flooded. Okay, but even though this cell is flooded, we have a path that we can walk. Okay, from my top to bottom. So I can start from here, I can reach to bottom, or I can start from here, I can reach to bottom. Okay, I can start from here, I can reach to the bottom cell, like basically the bottom row. Okay, or maybe from this to this. Okay, so I have multiple ways to do it. Okay, so day 1 I'm good, I can still reach from the top row to the bottom row. Okay, so let's go to day 2. Okay, so day 2, 2 1, this cell becomes flooded. Okay, now whatever path I was taking from this cell, okay, I cannot take now, because since I cannot traverse in diagonal direction. Okay, so for this cell, this path and this path, this is blocked, which means I can only start with this cell. Okay, so again from this cell I can go to directly to the bottoms. Okay, or I can go from here to here, or I can go from here to here. Okay, basically I'm reaching the bottom row still. Okay, from the top row to the bottom row I can still reach. Okay, cool. So this thing is also done. Okay, now let's look at day 3. Okay, so on day 3 3 becomes flooded. Okay, cool, which means this direct path that I was taking, that I cannot like now I cannot take that, right? Cool. So but still I can reach the bottom cell by moving to this path. Okay, or by moving to this path. Okay, so there is still a way I can do it. Okay, cool. Now let's look at our 4th day, which is this 2 2. So on 2 2 like on day 4 2 2 cell becomes flooded. Now if I observe, if I am starting from here, there is no way I can reach to the bottom. Okay, I will be stuck at here. Okay, and all the paths for this cell are blocked. I cannot reach at all. So yeah, so that means up to day 3, okay, I'm good. That means 3 days I can survive, not survive, basically up to 3 days I can reach from the top row to the bottom row. Okay, so 3 is my answer. So yeah, that's the question. So basically we have to process the days. Okay, and then we have to see whether we can reach the top row and the bottom row. Okay, we can do it in an increment order. So if I draw out a brute force, okay, so basically I will write like what's the gist of this answer. Okay, so answer is basically saying up to which day in my cells array, okay, I can reach, or I can say from up to which day there is a path from top row to the bottom row. Cool. So yeah, this is the question, and we have to solve it. Okay, so if we simply think of a brute force way, okay, how to solve this. So this problem is basically kind of a graph problem only. Okay, so we can do something like this. Okay, I can iteratively iterate over all the days. Okay, so I will say for d in range this len of cells. Okay, basically cells, the length of cell basically represent the number of days. Okay, now what I can do is I can select the prefix of my days. Okay, I can say so I can put a claim that up to d days I can survive. Okay, or like there is a path that reaches from the top row to the bottom row. I will claim that, then I will check using one of the DFS or BFS algorithm whether there is a path exists from the top row to the bottom row. Okay, so what I'll say is selected cells, I can put something like cells D. Okay, I will use the first D units. Okay, then I will check whether there exists a path from the top row to the bottom row. For that, what I can do is I can create a grid matrix. Okay, and in that grid matrix what I can do is I can fill all the cells that are flooded. Okay, I can fill all the cells that are flooded using whatever selected cells I have. Okay, then I can apply a DFS or a BFS approach. Okay, in order to check whether there is a path from the top row to the bottom row. Okay, check whether there is a path from top row to bottom row. Okay, so if there is a path, so let's say this give me something true or false. Let's call it all. Okay, so I'll say if all okay. Okay, I'll continue. I will keep on checking. I will keep on incrementing my d because I need the maximum day, right, up to uh, what up to the last day, which means basically I need the maximum d up to which my there exists a path. Okay, otherwise I'll break out of this loop. Okay, and whatever maximum d I have gotten, I will simply return that. Max d I have reached. Okay, cool. So this is kind of the pseudocode, or you can say the gist of the algorithm in order to solve this. Okay, but there is a problem with this problem with this. Okay, like with this you will be able to solve it, but as per the constraints, this will give you a TLE, because here if you see, I have this d, right, which is like basically iterating over the number of cells. Okay, so I have to iterate over the number of cells. Okay, which basically represents number of days. Okay, now per day I have to select all the cells. Okay, till that day, and I have to update my grid metrics, which basically means I have to initialize a grid. Okay, put all the rows and columns which are flooded with one. Okay, that means the number of selected cells that I have. Okay, and at max this can go to the number of cells itself. Okay, so I'll say per cell iteration I'll be doing number of cell iteration. Okay, this is for grid update. Okay, then after this I'll be running this BFS and DFS loop, which basically I'll start from all the cells which are not flooded in my top row. Okay, I'll put it in the queue if I'm running a BFS. Okay, or for DFS I will recursively traverse over them. Okay, and then I will traverse and I will check whether I can reach the bottom cell or not. Okay, with that I'll be touching all the cells. Okay, which basically means number of rows times number of columns. Okay, cool. So per day, like for this for loop I'll be doing this two uh, iterations, right, which is number of cells for my grid updation and row times call iteration for my DFS and BFS. Okay, so this will be my brute force approach. Okay, so if I look at the time complexity, okay, so here as per the constraint, the cell's length is equal to row times call. Okay, so whatever is the dimension of this matrix, okay, the number of cells in that grid, that will be the length of my cells array. Okay, so this I can replace with number of calls and rows and calls. So I'll say rows and calls. Okay, times, again number of cells I can replace with rows and calls, rows and calls. Okay, then there is again rows and calls. Okay, so this will be two times, and basically I'll be doing rows times number of calls square. Okay, now if I look at the constraint, the product of rows and calls, that is lying between 2 times 10 to the power 4. Okay, so if I put that value 2 times 10 to the power 4 whole square, this will give me 4 times 10 to the power 8. Okay, since we have to do nearly billion number of operation, this will go to a TLE approach. Okay, so how to do better? Okay, how can we optimize it? Okay, so we have been given this liberty in the product of rows and calls. Okay, so if there is a way I can reduce this thing, okay, I'm still okay. Okay, because this is will be what, 2 times 10 to the power 4. Okay, if I can reduce it, like bring it to from a linear, or like from a quadratic time complexity to something better, okay, I can do it. Now the first idea here will be, so just imagine, okay, so the number of cells that I have been given is basically the number of cells in the grid, right? Cells length is basically the number of cells in the grid, okay. That means you can think of, like, if I plotted a graph here, okay, let's say it's a 1D graph, and let's say this represents my days, okay. So when I did this dry run, we observed that up to certain number of days, okay, there is a path from top row to bottom row, okay. After a certain point, I cannot do anything, okay, there is no path exist. That means if I plot like 1 to up to the number of days, or this will be row times columns, okay. So I will have some green ticks for some days, like there exists a path, but after some iterations, okay, I won't get a path, okay, my paths will be blocked, okay. So the days thing will appear something like this, okay. That means I can I just need to search for a day after which I'm getting all reds, okay. So with that in mind, I can think of a binary search way, okay. What I can do is this for loop that I have, this parent for loop, okay, that I can replace with a binary search approach, okay, such that like it will help me to find which ith day, okay, there exists a path, okay, from top row to bottom row, and it's the maximum day itself, okay. So the modification to the pseudocode will be, I'll put my limits, okay. So what's the least day I can say, like there exists a path which is day 0 itself, right? Because on day 0 everyone is land cell itself, okay. Then the maximum answer I can get, okay, that will be the number of cells itself, okay, which is length of cells that I have been given, okay. Now this for loop I can update with a while loop, or like it's on you how you guys are implementing binary search. But yeah, it's basically the structure will convert into a binary search, and what I will do is while L is less than equal to R, I will have a ans variable, okay, to store the maximum day I can survive. I'll initialize to 0, okay. I'll calculate the mid value, okay. I'll say mid equal to R minus L by 2, okay. Now what I will do is this D I was using to slice the cells, okay. Now this D will be replaced with the mid value that I'm getting from the binary search, okay. So whatever things I was doing here, okay, those things will be replaced with basically the binary search structure, okay. Here selected cells will become cells up to mid, okay. Now from this I'll check, okay, I'll perform the this checking algorithm, okay. I will call it check algorithm, okay, to check whether there exists a path from my top row to the bottom row, okay. So if my check algorithm gives me yes, there exists a path for this day also, okay, then I will store that answer, okay, and I will look on the right side, which basically means I will move my L to mid plus 1, okay, and I will keep on looking on the right side. But let's say if I am somewhere here, okay, in this zone, that means my check algorithm will fail. It will basically say that there is no path exists from the top row to the bottom row, okay. That means I have to reduce the slicing amount, okay. So for that I'll be doing R to mid minus 1, okay. So basic binary search algorithm, okay. So yeah, from a linear time complexity here, okay, I will be getting logarithmic time complexity. Okay, so if I substitute this thing now, okay, this will become, okay, I can say the binary search uh, time complexity. Okay, so with the binary search, what I will do is, okay, this number of days, okay, this will be converted to log of number of days, okay, which is basically number of cells, okay, and which is basically the product of rows and calls. Okay, now per binary search iteration, I'll be doing uh, this thing, the grid updation and the DFS and BFS check. Okay, so with that I can say 2 times number of rows plus times number of columns. Okay, like as I discussed here, right? So this one row times calls I need for the grid update, and this row times calls I need for my DFS and BFS approach. Okay, which one I'm doing, like whichever one I'm doing. Okay, so yeah, now I'm not traversing all the cells, I'll be traversing over log of that iteration. So this will be 2 times 10 to the power 4, okay, times this will be log of 10 to the power 4. Okay, so if you observe, what will happen is, so I know 2 to the power 3, like sorry, 10 to the power 3 is less than 2 to the power 10. Okay, which basically means if I go to 10 to the power 4, okay, this will be approximately somewhere between maybe 10 to the power 2 to the power 15 or something. Okay, so this log of 10 to the power 4 will lie between 10 to 15. That means within 10 to 15 iteration, I'll get my number of days. Okay, so this log of 10 to the power 4, okay, this will be, we can take the max, okay, somewhere upon about 15 iterations. Okay, so 15 iteration times 2 times 10 to the power 4, okay, which will be like some 30 times 10 to the power 4, which will be what, 3 times 10 to the power 5. Okay, which is much better than a billion number of operation. Okay, and we will be getting acceptance. Okay, so this is a binary search and BFS or DFS kind of approach, and we can do that. Cool. So with that we'll get acceptance. Okay, but I'll show you one more approach, okay, in order to solve this. But before that, I'll show you like you can get acceptance with this approach. Okay, so I will quickly code up the binary search solution. So I'll code in Rust, okay, but the logic and everything you can apply in any language, so that's fine. Cool. So first I will store the number of rows in usize format as usize, and let calls equal to call as usize. Okay, I have been given in i32 and call. Okay, I don't need to use this as usize every time, so I'm just creating this variable. Then I will have this check algorithm. Okay, I will name it can reach. Okay, and I will create a lambda function that takes a day. Okay, and I will say usize, and it returns a boolean variable. Okay, and I will write my BFS here. Okay, I think BFS will be easier here. Okay, then yeah, then I will write my binary search approach, like binary search algorithm. So I'll say let mut l equal to 0, and let mut r equal to the number of cells or the number of days I have been given, cells dot len. Yep. Then I'll say while l is less than equal to r, I need one more variable for my ans. I will say let mut ans equal to 0. Okay, and finally I'll be returning ans. Okay, so yeah, here I will calculate the mid value. I'll say mid equal to l plus r minus l upon 2. Okay, then I'll say can reach if with this mid value or the day. Okay, I can reach, or I have a path from top row to bottom row. Okay, I will update my answer to this mid value, and I will look for higher values. Okay, otherwise I will reduce my day value, which is mid minus 1. Okay, cool. Now with this will be use size, answer will be use size, but I need to return either do. I'll say either do. Okay, now I will implement this can reach function. Okay, so here I will create my matrix, but I will call it graph. Okay, I'll say vec of vec. So on day 0 all of them are land, so 0, and yeah, I'm basically creating a matrix. Okay, where all the values are 0. Then I'll create a queue, so let mut queue. So in Rust we have to use dq, so it comes with a collection package, vec dq. Okay, so here I will say I'll be storing the position, which means I can use a tuple or maybe another vector inside this dq. So this dq will store a vector of usize elements. Okay, so I will initialize it, vec dq new. Okay, now what I will do is, for this day value, okay, so whatever, so basically this is the slicing part here. Okay, I will put all the like basically I will update my graph. Okay, I will update the cells which are flooded till this day. Okay, I'll say for d in range up to this. Okay, so let position this cell position cells of d. Okay, so I'll say graph of pos of 0 minus usize minus 1. I'll say as usize. Okay, because this has been given in i32, so I need to convert it into usize. And similarly for my column, so pos of 1 as usize minus 1, and I will say that okay, this cell has been flooded. Okay, now once my graph is updated, then I will update my queue. Okay, so I will put all the cell value in my top row which are not flooded. Okay, I'll say for call in range 0 to calls. Okay, so if graph of my first row and this column position, okay, is still land, I'll push in my queue. So push back vec of 0 and this call value. Okay, so these will be my starting cell from which I will run my BFS. Cool. Then yeah, for my movement I'll be creating a direction matrix. I'll say let drs, so vec minus 1 0 1 0 and minus 1. Okay, so how this will help me is, so I'll use this value and this value. So this will be, this two value will be added to my current row and column. Okay, and if you look at this pair of values, okay, this value is basically saying my row will be subtracted with 1 and my call will be added with a 0 value, which basically means I'll go up. Okay, then if I look at the next pair, here my call will be added plus 1, row will be added 0. Okay, so this is the right direction. Okay, then my row will be added with 1. Okay, call will be 0, down and left. Okay, so this is a cool way to implement cardinal positions iteration. So yeah, otherwise I need to create another matrix for the movement, so it's better to use this. Okay, so yeah, I'll say while q.len is greater than 0, so standard BFS algorithm. So I'll say let nodes, okay, in my queue. Okay, I'll say for this length of nodes. Okay, so yeah, here I'll be popping out my current land cell. So I'll say for my current land cell, this q dot pop front. Now this returns me option. I will simply call unwrap. Okay, because I know there exists a value, so I don't need to use some none. Okay, I can directly call unwrap. So this will give me the cell value which is currently my land, and from that I will collect its current row and column matrix. call position, so land 0, and let's see equal to land cell 1. Okay, then I will move in 4 directions. Okay, now one more thing, if this is popping out a land cell which is in my bottom cell, okay, then I can directly return true. Why? Because I'm starting with first row position. Okay, now in my BFS iteration, if I'm getting a cell value which has a row value of the bottom row, that means I have reached the bottom row, right? So that means from the first row, bottom row is reachable. Okay, so I'll say if r is equal to rows minus 1, then I'll simply return true. That means bottom row is reachable from up to like if my grid is flooded up to this day. Okay, then yeah, so what I will do is I can create another visited array. Okay, but I have this graph, so I can represent flooded cells with 1, and I can have another value to represent visited cell values. Okay, so what I will do is I'll say I can use maybe 2 for visited cell. I'll say graph of RC is equal to 2. That means I have visited this cell. Okay, then I will iterate over all the 4 direction. So for d in range 0 to 4. Okay, so my new r, let new r, this will become r plus drs of d. Okay, and let new c, this will become c plus drs d plus 1. Okay, so like I explained you the pair concept. Okay, so yeah, now I'll check if new r is greater than equal to 0 and new r is within bounds, so these are basically boundary checks, and new c is greater than equal to 0, and new c is less than calls, and the position is still a land. Okay, if this guy is still a land, I can say if new r and new c is still a land position. Okay, that means I will enqueue this in my queue. So I'll say queue dot pushback back of new r and new c. Okay, cool. Then I'll basically update my visited. I can update my visited also here. So I'll say graph of new r and new c as 2. Cool. So this will keep on iteration, and once I get bottom row cell, okay, I will simply return true. But let's say after all this iteration I didn't get any bottom row, okay, and my queue is finished up. Okay, then I will simply return false. Okay, so yeah, I guess that's all. I'll simply check whether I need to convert anything to U size. Okay, so DRS is initialized to I32. Okay, because that is -1, which basically means here this will get converted to I32. Okay, but this guy is U size, so I'll convert it to I32. And whenever I'm using these values are indexes, there I will simply say as U size. This is a pain in Rust where you have to convert this to I32 U size and all that. So yeah, cool. So this is the whole algorithm. So we have this BFS approach to check, and we have this binary search to find the maximum day up to which I can still list the first row and bottom row. So if I run this, cool, it threw me an error. So it says let found let statement not only supported if. Okay, unwrap expression expected expression. Okay, okay, yeah, let's run for all test cases, and I have this. Okay, yeah, I can convert, I can use these value now. Okay, let's be consistent, so I'll say I32. Okay, here also I'll say I32. Cool. Basically this value becomes I32. This was usize. Now cannot move index, uh, cannot move out of index. Uh, Move occurs because value has type I32, which does not implement the copy trait. uh, okay, so basically I need to pass a reference. So yeah, cool, all test gets passed. Now if I submit, and voila, it got accepted. Because this was the time complexity, okay, which was nearly 3 times 10 to the power 5 operation I'm doing, or like in the order of 10 to the power 5 operation I'll be doing. Okay, so time complexity wise, it was log of number of cells I have, which is rows times calls, okay, times the number of rows and calls I have, rows times calls, okay, a big O of that. Okay, and space complexity wise, okay, I'm basically creating this queue, okay, which can at max store all the cells itself, okay, which basically means all the position, which means row times calls. And I have this graph, okay, where I'm updating all the values, right? So that's again row times call. So a big O of row times calls twice, okay, which is in the order of row times calls itself. So yeah, and this is like constant, so I will not count that. So yeah, this is my time complexity for my binary search plus BFS approach. Okay, cool. So I have applied BFS. You guys are feel free to try DFS. Okay, BFS I thought like it will be easier. That's why I update. That's why I have taken this. Cool. Now there is another way in order to solve this problem. Okay, which doesn't start with this analogy. Okay, so it's because this kind of problem are pretty much there in when we are doing like earthquake analysis, flood analysis and all that. Okay, so there are certain papers also based on this kind of algorithm. Okay, so what another approach we can do is, so we call that approach offline uh, dynamic connectivity. Okay, so whenever you're so basically this problem is kind of a graph problem, right? Because your cells are making connections, okay, when the flood is filling. Okay, basically your land cells connection are getting like what cancelled out. Okay, your connections are closing when flood is filling, right? So basically this is a graph. Okay, and as your days are passing, your edges are keep on getting cancelling out. Okay, so whenever this kind of dynamicity comes into play, okay, we can use a very popular and very intuitive data structure, which is disjoint set. Okay, so DSU, disjoint set union. Okay, so this is a very powerful algorithm. Okay, it's so it's kind of my favorite algorithm. Okay, and it's very powerful because it does operate. So once you have a DSU kind of a data structure and you have the understanding, okay, all of the operation in DSU are in order of constant time. Okay, so whatever problem you have, okay, if you want to make it fast, okay, and yeah, your problem has some dynamic connectivity, that kind of approach. Okay, so you can think in the direction of DSU. Okay, and if it feels free, okay, like if it feels good to apply this algorithm, just apply this algorithm, because this is a very powerful algorithm, okay, on dynamic connectivity. So yeah, many algorithms where you apply BFS or DFS. Okay, sometimes it's better to think in the direction of disjoint set. Okay, and you will feel that yeah, you don't need DFS and BFS. DSU is much more intuitive. So yeah, so yeah, what we can do it here is, so so in order to apply DSU, okay, we have to look at the problem in the reverse manner. Okay, so by reverse manner, what I'm saying is, so whatever approaches we have discussed till now, okay, there we are going day by day. Okay, we are in a going through the days in an increment manner. Okay, which means we are looking for, so as we are going, that means we are getting flooded cells more and more. Okay, and our land cells were decreasing. Okay, so if I draw out some kind of a relation, okay, so let's say this is my land cell, okay, and this is my flooded cells. Okay, so with respect to time, okay, the amount of land cell, okay, initially they are higher. Okay, but as my time increases, okay, my flood cell becomes more. Okay, and my land cell basically decreases. Okay, and finally all the cell becomes flooded, and yeah, that's the story. This is with respect to time. Okay, so what this offline dynamic connectivity stuff tells that, okay, so start thinking in the reverse manner. Think that all your cells are already flooded. Okay, so go in this manner. Okay, so think all your cells are already flooded. Okay, and then do your iteration in a reverse manner. Basically means like do your iteration and get more land cells instead of flooded cells. Okay, so what that like what's that mean is, so if I draw out this, okay, so what I will do is I'll basically fill all these cells into water. Okay, then I will iterate over the cells, okay, in a reverse manner. That means I will first open up 3 and 1. Okay, that basically means so 3 and 1, I'll open up this cell. Okay, so what I will be saying is I'll start in the reverse manner, which means I will cover land masses. Okay, I will move in the direction of where in my neighbor I have land cells. Okay, and by that I'll be going. Okay, now here one more thing to apply here is, so in this connectivity algorithm, okay, we put some virtual nodes. Okay, so how this virtual nodes will help me is, so the idea is for this kind of cell, okay, I will add two nodes, one at the top, okay, and one at the bottom. Okay, okay, so these virtual nodes are not present in the grid. Okay, these are only for my DSU data structure. Okay, and how they will help me is basically in a DSU kind of a data structure, you can like if you guys are not familiar with DSU, uh, I will say graph. Okay, read an article. Okay, and you guys will have an idea. But yeah, basically we have a find and a merge method in that data structure. Find basically says that who is the parent of this node. Okay, and merge basically connects two nodes. Okay, basically makes a new edge between two nodes. Okay, so that's the idea. So what I will do is my the concept here is this top and bottom. Okay, I will only connect the rows of my bottom cells to this bottom virtual node. Okay, only when um, connect bottom row cells when they become land. Okay, so why they will become land? Because I'll be iterating over the cells in a reverse manner. Basically I'll be unflooding or like transforming the flooded cells into land cells. Okay, so yeah, So whenever any bottom row, okay, becomes a land, okay, I will connect it with this node. Basically means that node or cell will have this node as a parent, okay. Then similarly for the top cell, okay, again this is also a virtual node, okay. Whenever any cell, okay, from my top row, okay, they become a land, I will connect with this node, okay, something like this. Similarly these nodes will have a connection like this, okay. Now the same concept here also, I'll connect the nodes, connect top row nodes, okay. By nodes I mean the cells, okay, with this node when they become land, okay. So yeah, so I'll be connecting this node, like this cells when they become land, to this node. I'll be connecting the bottom row cells, okay, when they become land, to this node. Also whenever any cell in between them, okay, they become a land, okay, I will traverse over all the four direction and look for other land cells, okay, and I will connect with this cell the adjacent cell, okay, if they become land. So how this will help me is, since I'm connecting my top and the bottom, okay, they will slowly start to merge together at one point of time, okay. Now whenever I can claim that my parent of top is same as the parent of my bottom node, okay, for whichever day, okay, okay, that day will be my answer, okay. So yeah, that's the idea. So basically I will have a DSU data structure, okay, to make this connections, okay. I will start this cells in a reverse manner, okay. I will keep on unflooding the cells, okay, and for every cell, okay, I will iterate over all the four direction. If those have become land, I will connect with my I'll basically merge those cells, basically have an edge for the neighbor cell, okay, and my current cell, okay. And as I'm keep on doing that, okay, finally on one day, okay, I will find a connection from my top to the bottom, okay. So whichever day that is my answer, and that will be max because I'm iterating over in a reverse manner. So yeah, that's the logic behind DSU. I guess it's better to if I code and I will show you guys, okay, and in that I can explain you, okay. Cool. So in order to apply DSU, I'll be creating a DSU data structure, okay. So struct DSU. Now I'll create two data structure. So one is parent, to store the parent of every node, okay. So back of usize, okay. Then I'll create a size, okay. So this is standard DSU implementation, okay. Now I'll implement the two methods in DSU. So one is so yeah, first of all I need to create a constructor. So I'll say func new so it takes a value, okay, to have the capacity of size and parent, okay. So let's say size and parent, it returns DSU element, an object of that, okay. So I'll say let mut parent, I'll initialize to the capacity n, okay. Then for I in range 0 to n, okay, I'll simply push, okay. So initially in DSU every node is a parent of itself, okay. Now yeah, I think one more thing like you guys might be confusing here is like I have this cell, okay. what I'm pushing here, okay, because I have initialized like a U size, okay, I'll be pushing ID of this cell, okay. Now finding the ID of a cell in a matrix, it's pretty easy, okay. So just have this mind, you can write it somewhere, just learn it, okay. So let's say this cell position is row and R, okay. So this same algorithm is used in like popular plotting library like matplotlib, seaborn, whatever library you are using, the same algorithm is being used whenever you are doing this thing, okay. So yeah, let's say this cell has a value of RC, so its ID will be given as row, okay, the current row times the number of columns I have plus the call position, okay. This is my ID, okay. So it's a standard, so it's not like I have made something, it's a standard thing, okay. So how this will help me is, so let's say I have this cell, okay. So um, 0 okay. So or maybe I can draw for a big matrix. So let's draw for 3 cross 4, okay. So I have 3 rows here, 3 columns, four columns here, 0 1 2 3, 0 1 2 3, okay. This cell will have a ID of 0, this cell will have a ID of 1, similarly 2 3 4 5 6 7 8 9 10 11. Simply put this cell position into this formula, you will get these numbers, okay. So yeah, this is how we give the id value to each cell, okay. So yeah, what I'll be pushing is, so whenever I'm saying this parent, okay, I'm pushing the nodes, I'm basically pushing the ID there, okay. So I'll show you. So yeah, parent has been initialized, and one more thing I need to return is the size array, okay. So I'll say parent is parent, and my size array is a vec of all size 1, okay, initially, and I have n of them, okay. Cool. Then I will implement my find method, which is like finding the parent method. So it will take a mutable reference, um, yeah, takes a mutable reference of the object because I'll be updating the parent, okay. Then we have self, then the ID value for which I need to find the parent, as usize, okay. Then usize, okay. So I'll say while I haven't found the parent, which basically means the this guy is parent, okay. So so you guys can read the article like how to find parent and merge nodes, okay. It will be a very long video if I start explaining them, but yeah, the idea is as long as our node parent is not itself, I'll keep on iterating, okay. So here now I will apply some path compression algorithm here. Parent of x will become self of parent of x, and x will become self of parent of x, okay. And finally I will return self of parent of x. I can return x also, so both are fine. This is, so yeah, cool. Then I'll return I will create merge function, okay. So this merge will take two cell IDs, okay. I'll call it A, it is of size u size, B of size u size, okay. Then for merging, I'll first find that parent. Parent of A will be self of find parent of A, then let mut of self of B of find parent of B, okay. Then if both are having the same parent, that means they have an edge among themselves, so I don't need to do anything, I'll simply return out of that. Now if self of sizes of this parent is less than self of sizes of B's parent, okay, that means I need to merge A to B, that means A's parent will become PB, okay. So here I will simply or to reduce the code, I can simply swap the values. Okay, swap mute of PA and mute of PB. So these are like standard, so I'm not making anything new. Okay, these are standard DSU algorithm stuff, so you guys just have a read. Maybe I can make a separate video explaining how DSU works, but yeah, these are standard stuff in DSU. So size of PA, I will add it with self of sizes of PB. Cool. With this, I'm done with my DSU. Now how I will be applying it is cool. So again, I'll be collecting the rows. So row as use size, and let calls as call as use size. Okay. Then what I will do is, since I'll be storing the IDs. Okay. So I need a metric. Okay, or I need a data structure that can tell me if I give you this cell ID, whether that whether that cell is a land or it's flooded. Okay, so I can have a data structure that can tell me whether that cell value is a land or not. So this will be a mutable value. So I'll say is land, and this is vec of so initially I'm starting from the end, so that means everyone will be not land, so false. Okay, then I'll start with n. Now here n will be the maximum cell ID I can get, which is basically row times column. Okay, as you can see here. Okay, so the maximum cell ID can get is row times calls. Okay, cool. Now for my two virtual nodes, okay, which are not present in the cell, okay, what I can do is I can give this guy n as the cell ID. Okay, because you can see all the cell IDs, okay, they are varying between 0 to the number of cells I have, which is row times calls, okay, -1, right? So I can have row times calls for my bottom node ID, okay, and n+1 for my bottom. Okay, so I will just add the ID. So my top virtual node ID will be n, and my bottom virtual node ID will be n+1. Okay, so in this is land, I can initialize to n. Okay, then yeah, now I will create my DSU data structure. So my DSU takes the number of cells I have, so which is DSU new of it takes n, so I'll pass n+2. Okay, because I need to consider top and the bottom, because I'll be using them to merge. Okay, so this becomes n+2. Now similarly, I will again create the direction data structure, which is vec of -1 0 1 0 and -1. Okay, cool. Then I will iterate over the cells in a reverse fashion. So I'll say for I in range 0 to cells length in a reverse fashion. Okay, let's collect the row and the call position. So let's call it RR. So let's stick to R. Okay, I'll say cells of I of 0, this -1 as use size. Okay, because these are 1-base indexing, I need to convert them into 0-base indexing. So yeah, as this is also use size. Cool. Now I will get the cell ID. Okay, for this current cell position, I'll get the cell ID. Okay, I'll say let's call it ID. So this is row times the calls I have. Okay, so I'll say calls plus this C. Okay, now from this cell, okay, this is my current cell. Okay, as I'm traversing backward, this cell was flooded. Okay, now in my iteration, I will unflood this. Basically, this cell will become a land. Okay, I'll say is land of this ID will be true now. Okay, this cell will be now a land. Okay, now I will, for this cell, I will iterate over all the 4 directions. So for D in range 0 to 4. Okay, now yeah, one more thing. So here itself I can merge my top and the bottom. Okay, by checking that if my current row is a top row, okay, and it has become a land, okay. So as I told you here, okay, once a top row cell becomes a land, I will connect it to my top, okay. So that means if r is 0, okay, if it's a top row, I will merge my current cell id with the top, okay. Or if my r is a bottom row, which is rows minus 1, okay, I will merge DSU of merge the id of my bottom row, okay. So yeah, so if this cell belongs to a bottom row cell, I'm connecting it to my bottom row, and I guess I'm not using merge. Yeah, I'm using merge and find. Okay, cool. So here, now I'm iterating over all the 4 direction, and I'll check. I'll get the new row. So let new row. Same stuff. So I'll convert this RR as I32 because this was the use size. I'll subtract directs of this. Let NC minus direction of d plus 1. Then I'll see NR. No, then I will basically perform the boundary condition. So I can stick to this. NR is greater than or equal to 0, and NR is less than rows, and yeah, rows needs to be converted into I32 because this has become I32. Then NC is equal to 0. Same stuff for column also. NC is my new column is lesser than calls of I32. Okay. And yeah, one more thing I can check, but I guess I need to get the cell ID first. So yeah, if my boundary condition are met, okay, for this new cell, I will get the cell ID. So I'll say let new cell ID. Okay. So from this cell, from this flooded cell, I have transformed into a land. Okay. From that land, okay, I'm going over all the 4 direction. Okay, and I'm checking whether these surrounding cells have become land or not. Okay, so in order to check that, I'll first need to get the cell ID. So that is nr times number of columns I have, calls. So I'll convert into this needs to be of u size, right? So nr as u size, okay, times calls plus nc as u size. Okay, so this is my new cell ID. Okay, let's say this cell ID. Then I will check if this cell has become land. Okay, if is land of this new cell ID. Okay, if this cell has become a land, then I will merge this cell with this cell. Okay, so I'll say DSU dot merge my current cell, which is this, with this neighbor cell. Okay, so yeah, like that I'll be proceeding. Okay, then after this for loop iteration, I can simply check whether my top node and the bottom node has been connected or not. Okay, if they are, then whatever cell ID I'm currently in, or whatever day I'm currently in, okay, so I can say simply day. Okay, so day, this I value I can convert it to a day. Okay, so this day is the one, okay, or this is the maximum day where I can still reach, or I can still have a path from my top row to the bottom row. So if DSU of find of my top, okay, if the parent of my top node, okay, is equal to DSU of find of my bottom, okay, then that means now there is a path. Okay, so I'll return my day as a iterative variable. Okay, now even after doing all this, okay, all this for loop iterations, okay, I'm still not getting anything. I can simply return a 0. So 0 like this. So yeah, this is the whole algorithm. Let's run it for test cases, and let's hope it doesn't break. It's already a long video and it's break. Cell is, oh yeah, so this is cells, and yeah, I hope it runs. Okay, I converted to, I started with RR here. So this is R, this is uh, C, yeah. Then direction here, NR and NC, and I'm basically running now. Cool. Yeah, mistake size. So let's be consistent. Okay, let's make it sizes, and I'm checking the sizes with the sizes, and yeah. Hmm. So find parent found for mutable reference this in the current scope. Okay, method not found mutable. So I check this. No method name find parent. Oh yeah, I don't know. It could have simply said like find parent is not there. Okay, one more error. Let's fix it. X equal to self dot parent cannot assign to immutable variable. Yeah, this needs to be mutable. Yep. Mute. Cool. So it passed for all test cases. Now if I submit, and voila, it got accepted. Now why DSU is a good approach? So, and yeah, before going that, so it may happen you guys are not understanding this logic here. Okay, that's mostly because you guys are not familiar with DSU data structure. Okay, if you guys once get familiar with DSU data structure, I'm not doing anything fancy here. Basically, I'm creating two virtual nodes, and I'm keep on connecting edges as I'm unflooding the cells. Okay, so as I'm unflooding the cell, at will like there will be a time at which I have clearly a path like this. Okay, so this is my bottom, this is my top. Okay, this cell will be connected to this as well as this cell will be connected to this as well as this. Now once I have this path, okay, basically what will happen is, since I'm merging my cell values, the parent of this cell and this cell, okay, they will be of same value. Okay, that I'm basically checking here. Okay, so nothing fancier. I'm basically using DSU functionality here. Okay, so this guy, so just read an article about DSU, things will be clear. Okay, now coming back to the point, why the DSU approach? Okay, so in DSU approach, okay, if I look at the time complexity here, okay, I have this for loop which is basically traversing over the number of cells. Okay, which is row times calls. Okay, now here I'm doing this merge. Okay, again this merge and this find operations. Okay, which is per cell iteration I'm doing this merge and find operation. Okay, now if you look at my merge, okay, it basically performing this find operation. Okay, and swapping and adding stuff. Okay, so basically this merge is composed of two find operations. Okay, so now if I tell you this find operation, so overally I'm basically my DSU time complexity basically determined by the my find operations. Okay, so per cell iteration, then I have this DSU find operation time complexity. Okay, now this, oopsie, now this find operation time complexity uh, is of the range constant time. Okay, so that's the beauty. Okay, so I have this path compression kind of a structure. Okay, which basically boils down this find operation to a alpha times number of nodes. Okay, so this alpha basically represent a mathematical function. Okay, we call it inverse Ackermann function. Okay, so it basically designates to a set of function which grows very slowly. Okay, so due to that, the merge and the find operation time complexity are comparable to constant time. So if I simply search for Ackermann functions, okay, so inverse Ackermann functions. Okay, so you can simply read here, okay, an inverse Ackermann function, which is alpha of n, an extremely slow growing function used in computer science, especially for analyzing algorithms like union find, which is another name for disjoint set union. Okay, so yeah, this time complexity of this find operation is alpha times node, which is similar to, okay, or very much comparable to constant time. Okay, that means my overall time complexity will become a big O of number of cells. Okay, now if you compare that with the binary search time complexity, okay, which was this log of row times calls times rows times calls, I have reduced this log operation. Okay, so yeah, with that, my overall time complexity with this DSU approach is basically big O of number of cells, which is basically row times calls. Okay, now as per space complexity, okay, so I'm basically creating this parent and this sizes, okay, which are of length the maximum ID I can get, okay, and which is of row times calls. Okay, so big O of 2 times row times call, which is in the order of row times calls. So yeah, that's the time and space complexity. So yeah, that's the idea. So this is how you can solve this problem using DSU, and it is much faster with that. Okay, now this I have implemented in Rust, okay, and it got accepted. I have the similar code writing for C++ also. So in C++ solution also, so you can see, maybe I can open the Rust solution again, do a little submit. Let's put it here. Okay, now if I open C++, okay, so similar to what I was doing in Rust, okay, the same thing I am doing in C++. Okay, here also I'm creating this DSU data structure. Okay, I have this find, then I'm creating this unite, which is basically my merge function itself. Okay, and same stuff, I'm just iterating over the cell values in reverse order fashion. Okay, then I'm just connecting any cell which has become land in the top row to my top virtual node, any cell in the bottom row which has become land, I'm just connecting with my bottom virtual node. Okay, and for my in between cell iteration, okay, all the 4 cardinal positions, I'm basically merging my current cell and my neighbor cell if they have become land. And finally I'm basically checking on which day my top and the bottom has been connected. That day is basically my answer. So yeah, this is my C++ code. Okay, so if I submit this, voila, this also get accepted. Now I'll finally show for Go. So same stuff, okay, and it's very much similar to C++. Okay, here also I'm creating this parent and size. I'm creating the constructor. The find method is pretty similar to Rust and C++. Okay, just syntax different, but logic is same. Here also I'm doing that path comparison thing. Then I have this union. Okay, I'm just using different names. So yeah, but yeah, it's basically the merge function itself, nothing fancy. Okay, and here also I'm iterating over the cell in reverse order fashion, uh, merging my uh, land cells, which are like cells which are in my top row, which are being converted into land, to my top virtual node. Then similarly, whichever cells in my bottom row has been converted into land, I'm connecting it to bottom row. Then all my intermediate cardinal positions, I'm basically iterating over them. If they have become land, I'm connecting my current cell with those cells. Okay, and after that I'm finally checking whether my top virtual node and my bottom virtual node has been connected. If they have been connected, then that day value on which they have connected, that's my maximum value, because I'm traversing in a reverse order fashion, right? So yeah, so on the first day where these two get merged, or like these two have the same parent, okay, that will be my final answer. So yeah, this is my Go code. If I submit, and voila, it got accepted. So yeah, that was all. So it was a pretty good problem. Okay, if you think in the direction of binary search and BFS. Okay, but if you think in the direction of DSU, okay, this is pretty simple, because if you look at the binary search solution, okay, it has more code line, but in a DSU solution, it still has some code line because of this data structure implementation, but the application of that, it's only few lines of code, like nearly 40 lines of code. So yeah, that's the idea. So yeah, I hope you learned something new. If you like this video, please do subscribe to the channel, and please add some comment. Okay, if anything you have a problem, or some part you are not understanding, okay, it will help me a lot just to provide me some feedback, okay, where I'm lacking, okay, or from which part you didn't understand. I will improve upon myself. So yeah, I guess we are pretty close to New Year. Only few hours are left. So I'll just say Happy New Year, guys. Stay tuned to watch more videos. Bye bye.